Would it be? Because today we are covering tidy data. Okay, so
That's not regular expressions.
what's that?
I thought we were doing regular.
Next week. Next week's regular expressions. Okay. Sorry to disappoint. Yeah. Okay. So today we'll do tidy data. Monday we'll do dplyr, and then Wednesday and Friday we'll probably do regular expressions. Okay. Good stuff. All right. So let's talk tidy data. All right. So pretty much all of my stuff is coming from R for Data Science. This book. You can read it for free while you're at UCLA. You guys all know about ProQuest Safari Books Online, right? No, you guys are shaking your head. No, you guys are paying not a bajillion, but a lot of money for tuition, okay? And that money goes, well, some of it comes to me, right? Just a small sliver. But some of it goes to the library, right? And I don't know if you guys use the books at the library. But if you're like me, I don't go to the physical library very often. But your library money pays for the university's digital subscriptions to these digital libraries. And one of them is Safari Books Online, okay? So you guys know the O'Reilly company that publishes all of these programming books, right? You go to any, I guess bookstores don't really exist, but the UCLA bookstore has a section where there's programming, and there's a whole bunch of O'Reilly books, right? And if you want to buy these, or if you go on Amazon, you search for R books and stuff, they're like $50 each, okay? You can read all of them for free because you're a UCLA student. You have to be connected to the UCLA network. They look at your IP address, and so if you're at home, you have to VPN in. Okay, but if they see it's coming from a UCLA server, they'll say, all right, we'll let you read all of our books for free, okay? And so one of these is R for Data Science. You can buy it yourself. You can get the print copy for $40 if you want, or however much it is. But take advantage of your library subscription that you are already paying for, okay? So use that. Anyway. The only thing is you have to read it in your browser, right? And I don't know. That's how I read almost everything these days, so I'm used to it, but some people really like having a paper book, and I get it. Okay, anyway, this book, written by Hadley Wickham, Garrett Grolman, both, they work at RStudio, and Hadley Wickham is kind of the master of the tidyverse, okay? So the tidyverse is an opinionated collection of R packages designed for data science. All packages share an underlying design philosophy, grammar, and data structures. And so how can a collection of packages be opinionated? But the idea here is the data that you work with, they have the opinion that they should be formatted a certain way, and that the way you interact with them is done a certain way, okay? It's kind of, I don't know, if you take a cooking lesson from a master chef or something, they will probably have very strong opinions on how you should hold your knife, how you should wield your knife, and things like that, right? And so Hadley Wickham, the master of R, has strong opinions on how we should interact with data, okay? And so he's created all of these packages. Some of these we've already talked about, and others we will cover later. And so this course, I guess because I got to choose what to cover, I'm very much a believer of the tidyverse, okay? Of course, I still use base R. I still use base graphics all the time, but we'll cover ggplot. We'll talk about Tibble and tidyr today. And then next week we'll look at dplyr and stringer. We've already covered reader. We won't get into per or forcats, okay? But these are all kind of dealing with different aspects of your R data, okay? And anything you want to do, you can go to the tidyverse. Is it tidyverse.org? Just type in tidyverse in the internet and you'll find it, okay? and you can read about it. All right, and so kind of one thing that we're going to be working with is called the Tibble. Okay, the Tibble's a data frame. Okay, it's a data frame, but it's been tweaked. Okay, so there's a few things in data frames, like for instance, when you create a data frame and you've got character information, the default behavior of data frames is to turn them into factors. Okay, and that was probably useful a while ago, not so useful now. Okay, when R was first designed, computers had very limited memory, and so storing all the character information took up a lot more space in memory than converting them into integers, right? And so factors convert characters into integers, and that takes up less space in memory, and that was advantageous back then. But today, who cares? So, and now you run into problems when you have factors, when you're trying to like combine factors and stuff, you get into all sorts of issues. So anyway, the Tibble changes some of the stuff, okay? And then it also improves different things. One of the things is how it prints, okay? So here is just a simple data frame or Tibble that we are creating, okay? And then so the way you make a Tibble is you just type in Tibble, okay? Just much like the way you create a data frame is you go data.frame and you list off, you know, x equals this thing and y equals this thing and z equals this thing. With the Tibble, you just say x equals this, y equals this, same thing, okay? Same kind of structure. Here we're just, we're creating 1,000 rows, okay? 1 through 1E3 is, so this is the integers 1 through 1,000. We're asking for 1,000 random uniforms, sample the letters 1,000 times, and we're just putting in like random dates and times here, okay? All right, so what is this gonna do? When we ask to print it, when it's a Tibble, a nice thing that it does is it's only gonna print the first 10 rows, okay? And then it only prints the columns that fit on your screen, okay? So I don't know what the exact specifications are for the, I guess we could fit column E here easily, but rather than kind of exploding your console, it's only going to fit the columns that fit on the screen. And then this is also very handy. At the very top, it lists off the data type, right? So it'll tell you, oh, okay, this is integer data, this is double data, this is date, and this is date time information, and all of that stuff. Whereas, here, let me see if I can, okay, so let me see, data diamonds. Okay, so we'll bring that in. Okay, so if I just type in diamonds, so this is what it looks like as a Tibble, okay? So we've got these columns, and it only shows this, and it says with 53,930 more rows, right? If I do as.data.frame and I ask to print out diamonds, I think you guys experienced this, right? Where just prints out a whole bunch of stuff onto the screen, okay? And sometimes that's inconvenient. And especially if you're working in a situation like this where, you know, maybe your screen size is limited, okay? And if you do as.dataframe diamonds, it's gonna print out like rows here, like we're getting 100 rows and it prints out these columns that fit, and then the next set of columns spill over, right? Whereas diamonds is a Tibble, and it's only gonna print the columns that fit on the screen and say, you know, there's more columns and there's more rows, okay? And so, so that's really nice. Okay, it's a nice feature. Okay, and then the other thing is that Tibbles, when you subset them with single square brackets, it's always going to return a Tibble. Okay, and we haven't gotten into object-oriented programming. That will come in a couple weeks. But you can see a Tibble, the class of a Tibble is a data frame, but it's also got Tibble df and Tibble on top, okay? And so when you subset with a single square bracket, it always returns a Tibble, okay? Whereas, but unless you specify drop equals true, where it will drop down. Whereas the data frame, if you select a column using a single square bracket, it's going to simplify down to the whatever that single column type is, right? So data frames are, when you use a single square bracket, if you select multiple rows, you're going to get class data frame. If you select multiple columns, you're going to get class data frame. But if you select only one column with a single square bracket, it's going to simplify down to integer. Okay? So the behavior of the single square bracket differs. Whereas with a tibble, the single square bracket will always return a tibble unless you specify drop is true. Okay? And then, of course, if you want to select a column, you can always use the double square brackets or the $ notation, as you do traditionally with data frames. Okay, so those are just some differences with tibbles. Okay. All right, and today the focus is going to be talking about tidy data. Okay, and so tidy data is governed by these three rules. Okay, every variable has to have its own column. Every observation has to have its own row. Okay, and then each value has to have its own cell. All right, and so this is the rule of tidy data, and I think this is kind of what we're accustomed to, but sometimes we encounter data where this is not the case, and that complicates the way we do our analysis. All right. So here is an example of tidy data. So this is data on, I guess, some tropical storms, okay? So we had Storm Alberto and Alex and Allison and stuff like that. And I guess you have the wind column, which is wind speed. Pressure is in, I don't know, something. I don't know how pressure is, millimeters of mercury or something, or bar or Pascal, I don't know, right? Okay, something, right? And then the date that this storm happened. So this is an example of tidy data, all right? And if you look at it, each of the columns, storm name, wind speed, air pressure, and date, each of those variables get its own column, okay? So we have one column for one variable. So that's good, that's tidy data, okay? You might see data like this, okay? This is not tidy, okay? This is not tidy. Because if we look at it, what are the variables represented here? I mean, we could argue that each variable gets its own column. There's a variable 2011 and a variable 2012 and a variable 2013. I guess that's technically okay, variable country. But 2011, 2012, and 2013 are really better described as one variable, and what's that variable? The year, okay? So if we have the variables country, the variable year, and what's this last thing? Just the value of whatever we're talking about. I think this was like, I don't know, cases of some disease, okay? And so if we think of how this data is arranged, okay, we've got the country going like this. This is one, the country has its own column, but the year is spread out across the column headings, okay? And then the value or the counts are kind of distributed around here, all right? And so that's not tidy, okay? You may also run into a situation like this, okay? What are the so right now we've got the variable city, particle size, and amount, okay? How many cases or how many observations do we have? There's 6 rows right now, but maybe it's better to say New York is one observation, London is one observation, and Beijing is one observation, okay? And if we say that there's only actually 3 observations, then what are the variables that we have? Is this a way too confusing question here? What's that? So we got, okay, so we're going to say 3 observations. One of the variables is going to be city, okay? And then what are the other variables? small particle and large particles, okay? And so this is what we've got. We've got the city, and then we've got the amount of large particles, which is stored in the same column as the amount of small particles, okay? And so somehow we want to kind of separate these values out, okay? And so, this data you can get online on GitHub. It's on on some stuff. So I'm just reading them in using read_CSV. Okay. So again, read_CSV will bring everything into as a tibble, and it kind of brings in, tells you all of this information. Okay. So I'm just bringing into the data into the storms table, cases table, and pollutions table. Okay. And when you have data stored in tidy form, you can run vectorized operations, okay? And this is one of the reasons why, one of the many reasons why, but one of the reasons why we like to deal with tidy data, okay? So for example, I don't know if this is even relevant in meteorology or whatever, the storms and stuff. We could calculate the ratio between wind speed and the pressure, right? So I could do pressure divided by wind speed, and I can do this vectorized, right? So I can just do storms $pressure divided by storms $wind, and store that into storms $ratio, okay? And that's going to do, 1007 divided by 110, that gives me 9.15. 1009 divided by 45 gives me 22.4, et cetera, et cetera, et cetera, okay? It just applies them exactly as we would expect in a vectorized form, and it's very quick and very fast, okay? Can you imagine trying to do something like that when you have the data, the different values you want stored in the same column? Like if you wanted to do the ratio of large particles to small particles when it's stored here. It would be very hard, okay? You would have to create some kind of subsetting thing where you're only going to select the odd rows and select the even rows, assuming that everything is large, small, which might not be the case, and then, otherwise you have to do a match where we don't want to deal with that, right? Let's get everything into tidy form, okay? Okay, so let's take a look at this table. This is the cases table, okay? We've got 3 rows, 4 columns, okay? France, Germany, United States are the rows, each country. And then we've got columns 2011, 2012, and 2013, and something like this. Okay, so if I tell you, so I want you guys to try this, okay? If I tell you that the columns, or the variables that we want, are the country, the year, and the count, and we make it tidy in this case. So each column, or each variable gets its own column. So country gets its own column, year gets its own column, and then the count, or the count of cases, gets its own column. What will be the dimensions of the resulting data? Okay, so think this through. And try to imagine what this resulting table will look like. And then if you want, you can talk to your neighbor to just confirm. So we're going to take this entire data set and make it a tidy data set where the variables are country, year, and count. So what are the dimensions of this resulting data set going to be? All right, turn to your neighbor and say, I think the dimensions will be... All right. Have you guys agreed upon something? Okay, what are the resulting dimensions going to be? What's that? 9 by 3, that is correct, okay? This is what the resulting data set would look like. Okay, so So basically, we would have the column country and year, okay? And this value 7,000 for 2011 in France will come here. And this value 5,800 in 2011 Germany will come here. This value 15,000 in 2011 US will come here. And then this value 6,900 in France 2012 will come right here, okay? And so each of these things get put together, and our tidy data will now have will now be 9 by 3. All right. Okay. And so we load up the tidyverse. Okay. And did I forget to mention this at the very beginning? Okay. You call in library tidyverse. Okay. When you call in library tidyverse, it's going to load up all of these packages. Okay. You can specifically just load in tidyr. Okay. That's the package relevant to what we're doing today. But you can just do tidyverse, okay? And so tidyr contains a function called pivot underscore longer, okay? So we use pivot longer because effectively we want the resulting data set to be longer than the original data, okay? Older versions of tidyr used to call this gather, but we call it pivot longer now, okay? And so we're going to say apply pivot longer to the data frame cases, okay, which is what we have here. And what we're going to do is we're going to gather the columns that are named 2011 through 2013, okay? Those columns, we're going to take those names and put them into a column called year. And then the values associated there are going to get thrown into a column called cases. Right. So the parts that you need for pivot longer are the specification of the data frame, okay, the columns that you're going to gather, and tidyr supports taking names and using colon notation, okay? So in our case, you can say, I want columns 2011 through 2013, and you can just provide names, okay? So even though it's in quotes and stuff, you can put a column. And so if you have columns like for months, January, February, March, April, May through December, you can do January colon December, and it will gather all of those month columns together, okay? Names too is just a string, okay? It could be whatever you want. In our case, it makes sense to use year. Values too will be is just another string, okay? And it gathers that, okay? So the names that you use, names to and values to, these are completely arbitrary. There's no reason why it has to be year. There's no special meaning to year or cases or amount or count or anything like that. So here I'm using kind of ridiculous names. When it happened and how many. Okay, and that would be terrible names to use for a data frame, but it's not wrong, and we still get the same result. Okay, we get 9 a Tibble, which is 9 by 3, 9 rows, 3 columns. Yes.
For the 2011 to 2013, does it matter? Like, do those matter, or is it just incrementing along the names of the columns?
It increments along the names of the columns. So it's if you use the colon notation, right? So the columns are listed in a certain order. It's gonna, whatever name this is, colon, how far you want it to go, right? So it's not like there's some internal measure, right? So if you do the names of the month, okay, it's gonna go, assuming it's in calendar order, January, February, March, April, May, so on and so forth. It's going to start with the first one and end with the last one you've got listed. Yeah, it's a very convenient feature. Otherwise, if you're not quite sure, if you need to specify, like you just want to gather certain columns and they're not all next to each other, then you can just provide a vector of either character names or column index positions. So you can say I want columns 3, 7, 9, and 12 gathered together, or something like that. Okay. All right, is that okay? So this is just the basic function of gather. So we've gone from here to here. All right, I'm sorry, not gather. Pivot longer. Okay. So here's a question. What happens? So here's our original cases data table, okay? And we've got the columns 2011, 2012, and 2013. What's going to happen if I pivot, if the columns I pivot are only 2012 and 2013? So I'm going to do pivot longer, and this time I specify columns 2012 through 2013. I'm only going to pivot those two columns. And we're going to keep everything else the same. Names 2 is year, values 2 cases. What do you think the resulting dimensions will be? What do you think this resulting table will look like? Number of rows first. All right, what do you guys think? Any guesses?
4 by 6.
6 by 4?
6 by 4.
Yeah. Okay. Indeed, that is the result. The result is going to be a 6 by 4 Tibble, and let's take a look at what happened. Okay. So 2012 and 2013 got put together. Okay, because we pivoted those two columns, right? So 2012 and 2013 got combined into the year column, okay? And those values, so here's the original values, 6,900, 6,000, 14,000, 7,000, 6,200, 13,000. Those values, 6,900, 7,000, 6,000, 6,200, 14,000, 13,000, those got combined, okay? And what we see is that the value for the ones that were not pivoted, those just get duplicated. So France gets duplicated, right? France, France, Germany, Germany, US, US. And then the value in 2011 just gets duplicated as well. 7,000, 7,000, 5,800, 5,800, 15,000, 15,000, okay? So basically anything that is not being pivoted is just going to get duplicated. And then the ones that do get pivoted longer, those values get combined into a single column. The values get combined to a single column, and then the column headings get combined into the names column. Does that kind of make sense? All right. Let's try this. What if I include country in the columns I pivot? Okay, so this time I'm going to do pivot longer, and I'm going to say I want to pivot from country, the column country, to the column 2013. It is a bad idea, okay? Okay, so obviously we wouldn't want to do this, but what will happen? What do you guys think will happen? I just want to make sure we understand this concept of pivoting longer into scenarios that are stupid. Okay, so what do you think the resulting data frame will look like, or table will look like? How many rows and how many columns? What's that? 12 by 1? 12 by 2 is what's actually, okay, so let me just show you. So first of all, when you do pivot longer and you try to do something like this, and in this case we've got numeric information and we've got character information, and then it's gonna say, I think you're doing something wrong, okay? So first of all, it's gonna throw in an error, okay? It's gonna say, we don't have a common type for country and the first variable that we're dealing with, 2011. It says you've got character info and double info, and we're trying to combine this. It's not a common type. I think you're making a mistake, okay? So there's some checks here, okay? A little bit of safety checks, okay? But let me just kind of go to what we were going to answer, all right? So I had to shrink this down. So I'm going to just convert the whole thing into a character data frame. Okay, so I lapply, as.character, and I turn the whole thing into a character data frame. All right, so now I'm not going to run into this data mismatch type check. Okay, and now I can still run the pivot longer. Okay, so I've converted everything into character. I do pivot longer, and so the result is going to be a 12 by 2. Okay, I've got one column of values, and then all the column headings get thrown into the names column. So it goes country 2011, 2012, 2013, country 2011, 2012, 2013, and then it goes France 7,000, 6,900, 7,000. And we've lost a lot of the meaning because we've done a foolish thing by trying to pivot longer one of the key identifying columns. Okay, but conceptually it did exactly what we told it to do. Okay, we said kind of take all of the values here and throw them into one values column and take the column headings and then combine them. Okay, and that's what it did. But we've lost a lot of meaning behind it. Okay, so we get a 12 by 2. Is that all right? For pivot longer. Okay. Okay, let's take a look at this thing. Okay, this is the pollution table, all right? And we've got New York, London, Beijing. Right now it's a 6 by 3, and we've got large, small, large, small, large, small, and then these things here. Okay, so the question is, if I want to make this tidy, what will the dimensions of the resulting data frame be? Okay, again, the variables are going to be city, large particle amount, and small particle amount. I think I gave this answer earlier, but the resulting data frame, if I tidy it this way, to say these are the variables, will be what? Okay. In this case, it's going to be a 3 by 3. Okay, we're going to take this value, New York 23 goes right here, and New York small 14 goes right over here. Okay, and we've got the column large and we got the column small. Okay, and so what used to be 6 by 3 will become 3 by 3. Right? And now I can do kind of those vectorized operations, and I can just do large minus small, or large divided by small, to get kind of the ratio of large to small particles, or the difference between large and small particles. We can do vectorized operations now that the values are stored in different columns, okay, or the different variables are stored in different columns. Okay, so what do you think the name of this function is called? So the other one was called pivot longer. This one's going to be called pivot. It's called pivot wider. Okay, pivot wider. All right. Huh? Does that make sense, right? Okay, so we've got. It used to be called spread, but we call it pivot wider. All right. And so so all we do is we say the names. The names come from this column size. Okay, so we say here's the column size, and we're going to draw the names from the column size, and the values come from the column amount. Okay, so we say pivot wider. There's only 3 arguments here. The data frame. We say the column where the values are coming from. I mean the names are coming from, and the column where the values are coming from. So we say the names, large and small, come from the size column. Okay, the names of the column headings basically. And then these values that we're going to distribute come from the amount column. Okay, and so this kind of just explains that. So that's pivot wider. Okay, all right, so pivot wider is sensitive to kind of spelling differences. Okay, so here I make a duplicate of pollution, and I intentionally mess things up, okay, by changing this first thing from New York to NYC. All right, and I'm going to run the same command that I did earlier. Pollution to, names from the size column, values from the amount column. What do you think the result will look like? Okay, So when everything is named consistently, this is what it looks like. Okay, you get a 3 by 3. But now that things are not named consistently, we got an NYC and we've got a New York. So if I pivot wider this, how many observations am I going to have? I will have 4, right? I've got 4 unique cities, basically. I've got an NYC, a New York, a London, and a Beijing. Okay? How many columns am I going to have? Still 3, okay? I'm going to have city, large, and small, okay? And so this is the result that we end up getting, okay? So when we pivot wider, it says NYC, there's 23 large, and we didn't find a value for small, so it puts in an NA. And New York doesn't have a value for large, so it gets an NA, and then there's 14 small, okay? And then the others get pivoted wider correctly as we would expect. Okay. All right. Another example here. So here, the cities are all spelled correctly, but here I have an all caps large for particle size. So what happens when I pivot this way? Okay. How many observations will I have? 3. How many columns will I end up having? 4. I'm going to have a column for all caps large, and then small, and then lowercase large. Okay. And so, you know, basically it's going to produce a row for every unique value in the columns that aren't being pivoted. Okay. And then it's going to create a column for every unique value that appears in the column that is being pivoted. Okay, and so it's important that your spellings are consistent. Okay, throughout the thing. And so if so this is where using a factor and only having certain levels allowed makes sense and stuff like that. And you can pivot it that way. Okay. We don't run into the issue when we are pivoting longer because, you know, if this was like 2011 and this was just like apostrophe 12 or something, it doesn't matter. It's just those values will just get duplicated, and it will look different here and look kind of funny, but it will just get consistently duplicated throughout. Okay, are there any questions on tidyr? Pivoting longer, pivoting wider. Okay, so I don't have a slide on this, but pivoting longer and pivoting wider are basically complementary actions, right? So there might be a case where you want to go from this back to the long form, right? And so you can go back and forth just by kind of pivoting longer or pivoting wider. And so maybe I'll just kind of demonstrate. So here's pollution, and so I can pivot wider pollution, and I got to do names from and values from. Okay, so this pivots wide. Okay, and then I can punch this back into pivot longer, and this is silly to do, but we're going to say, what is it? Names, not names two. The columns are going to be equal to large and small, and the names two is going to be size, and the values 2 is going to be amount. Okay, and they are complementary actions, right? So I can take the results of. So here's the wide operation, and I can just feed the wide operation into pivot longer and get back the original result, okay? Because they just kind of undo each other. So pivot longer takes everything and takes the different columns and puts them into one, and then pivot wider takes values in one column and puts them into many. Right? So you have that. Okay, we'll wrap up here for today, and we'll see you guys on Monday. Have a good weekend.